This chapter introduces several diode circuits, the most important of which are rectification circuits, which means that we're going to go from an AC to DC. Here we have a circuit with only one diode, and we are feeding an AC signal into the circuit, which means that only the positive side of the wave will get through because the diode only conducts in one direction. The result is a signal as shown in the drawing, where only the positive side of the AC signal has gone through the signal. Now, if the AC signal was 50 volts RMS, we need to find the peak. The peak voltage is found with a formula says that peak voltage is voltage RMS divided by 0.707. In this case, it would be 70.7 volts. We need to find voltage DC, which in this case is peak voltage divided by pi, in this case 22.3 volts. And the reason why that is important is because we're saying is that 50 volts RMS AC will equal 22.3 volts DC, and that this amount of voltage will produce the same amount of heat when put through 4.7 kilo ohm resistor. Here is our circuit with one diode, which by the way is called a half-wave rectifier, but this time we are including a transformer, a step-down transformer. The transformer formula says that the number of turns in the primary divided by the number of turns in the secondary is equal to the voltage in the primary divided by voltage in the secondary. But what we are looking for is voltage in the secondary, so we rearrange the formula as shown in the diagram. If we solve for voltage in the secondary, we find that the secondary voltage is 15 volts. This is the voltage that's delivered to the diode circuit. We repeat the procedure from the first problem to calculate peak voltage. Notice that peak voltage I must subtract 0.7 volts because I have one diode drop. Then of course I calculate DC voltage and find that it's 6.52 volts. The values we have calculated in this problem are lower. That's because the step-down transformer has lowered the voltage to much lower levels. We want to improve the performance of our circuit by using two diodes so as to create a full wave rectifier. The top diode conducts on the positive side of the wave. The lower diode conducts on the negative side of the wave. But because they're wired in a certain way, they both lead the current through the load resistor, and the result is the diagram that you can see. And this is called a full wave rectifier. It's also called pulsating DC. We begin by calculating secondary voltage, but notice at this time the transformer is a 7-to-1 step-down transformer. And when we calculate secondary voltage, we find it's 17.1 volts. The type of transformer we are using is called a center tap transformer, which means that the secondary has a center tap, which cuts the output voltage exactly in half. If everything is wired correctly, the output voltage now will be 17.1 volts divided by 2, which is 8.57 volts, and this is the voltage then that gets delivered to the circuit. We calculate the peak voltage and find it to be 12.12 volts, but the voltage actually delivered to the load resistor, is 12.12 volts minus 0.7 volts due to the diode drop. And then finally we calculate the DC voltage, which this time is 2 times peak voltage divided by pi, or 7.27 volts. Why 2 times peak? Because we have two little humps due to the full wave rectifier.